This is the first page of the Regents Review, and we're starting polynomial functions. The first question says, which of the following power functions best describes the end behavior, also known as long-run behavior, of the polynomial? So first off, a power function is any function in the form a times x to the b. So let me just erase that. And that's in contrast to an exponential function where we have the x and the exponent. So each of these are power functions. This is 3x to the first, and then the other ones, put a 1 in front of here, are in that form. So we know that the largest powered term, so in this function x to the fourth is the largest power, determines the end behavior. This has a coefficient of -3, so a negative number. So this function, the whole thing, is going to look something like this, where both sides point down. Because of the other parts of the function, this is a polynomial function because it has more than one term. There might be some loops in the middle, but the end behavior, the way the arrows go, is both down or towards negative infinity. So as we said, the part of the function that determines that is this term with the x to the fourth. So this is the power function, the single term function that determines the end behavior of the polynomial function that's up here. The next one is kind of similar, but we have to work from roots. So this is one you could do in your calculator, but we're going to talk about, if it wasn't multiple choice, how would we do it? So the first thing I notice is that this graph has a single root at x equals -5 and x equals +3, and there's a double root at 0. So that's as if we had two roots at 0, and this is a double root where it just comes down and touches and then goes in the opposite direction or is tangent to the x-axis. So if I'm going to rate this function, we know that the roots have the opposite sign of the factors. So if I have a root of -5, I have a factor of +5. And if we were going to solve this factor, set it equal to 0, it would go back to -5. So those two kind of go together. +3 would give me a factor of x minus 3. And then here I have x minus 0 and x minus 0. Now, both of these factors reduce to just x's. And if I put them together, I would get x squared. So currently I have the function, so these two become x squared, x plus 5, x minus 3. So that's from the roots. Now the other thing I noticed is that this end behavior of this graph is pointing down. So we count our x's, and we see that there's 1, 2, 3, 4. So this is acting like an x to the fourth graph, and it's acting like a negative x to the fourth graph because the two ends are pointing down. So when I look at my choices, I need to put a negative on. This would be the function. If I'd had a double root at either -5 or 3, I would have had a squared also on that particular factor. So that's where it would be. If both arrows had pointed up, okay, we would have had a positive x squared, so it would have been choice 4. And let me just erase this. The other two don't show the double roots. I'm just going to draw what those graphs would look like. This is 1, 2, 3, so an x cubed, and it's negative, so this graph would look something like this for the end behavior. This one, 1, 2, 3, and it's positive, so this one would look something like that for the end behavior. Those are cubic graphs. Moving down the page, the next question asks about identities. So looking at each of these, basically I want to see which one makes both sides equal to each other. So I'm going to multiply out the factored side. You could also factor the simplified side if possible. So I'm actually going to start with this one. It's pretty easy. So this one is 10x plus 5. That's not equal to 10x plus 6, so this equation is not an identity or something that is true for all values of x. Looking at this one, I need to write it twice. X plus 4, because we have addition, so I can't use the distributive property of exponents over addition. If I multiply this out, I'm going to get x squared plus 4x is plus 8x plus 16. and that's not equal to x squared plus 16. So that one's also out. Moving on to the next one, I'll do this one. So we're distributing, double distributing. I have x squared minus 9 equals x squared minus 3x plus 3x minus 9. So I see that these middle terms cancel, and this one does look like the identity. So I have x squared minus 9 equals x squared minus 9. Just to check this one, I already kind of see the issue, right? Because I can't distribute. The all 4 also doesn't necessarily make sense with the squared. So this one would give me x squared minus 4x is minus 8x plus 16. And this side would just give me x squared minus 4. So that one does not work. So choice 3 is the answer. Moving down to the next one, there's a couple different ways to do this one. So I'm going to show both of them. And in general in these videos, I'm trying to show as much to also review. So the one way we can do this to get it in this form, I notice this is a quotient remainder form, so I could use long division. So we have 6x minus 1 divided by 3x plus 7. We see how many times the 3x goes into the 6x, that goes in 2 times, and then we multiply. So we get 6x plus 14 down here. We're going to change signs. 6x minus 6x is gone. Negative 1 minus 14 is negative 15. So we're seeing that the number, so we would write this, the quotient here is 2. And then we write the remainder, which is negative 15, over this divisor. So that's 3x plus 7. Okay, so the number that's here in the place of b is the negative 15. Now there's a second way to do that problem, which involves splitting up this into 2 fractions. So I'm going to write that way over here. So the first thing we do is we compare the first 2 terms. The 6x is twice as big as the 3x. So I'm going to create something twice as big as the whole fraction. So just like the 6x is twice the 3x, I'm going to put a plus 14 on the top. Now I need to make it equal to this. So to balance out the plus 14, I'm going to put a negative 15 here. So this is called splitting it up into an addition problem, is one way you can think of it. This fraction, because the numerator is double, the denominator is equal to 2. And then we have the negative 15 over 3x plus 7 left. So this gives me the same answer as long division, it's just a different way to do the problem.